Hi everyone, welcome back to our lecture. Okay, so last week we learned about discrete random variable, and we learned about how to find the variance, how to find the probability mass function, cumulative mass function, and how to draw them plotted in graph and so on. So this week we are going to learn about discrete random variable. If you look at this graph, there are a lot of graph here. Basically, the top part, the green one, is actually those distribution to analyze the data that are discrete random variable data. So if you look at the data, they are actually probability mass function versus x. X is number of trial. So we are going to learn how to determine the probability and also how to find the mean and variance. So why we need to know the mean? Because we want to know the average. Where is the overall data, the value, the mean, average, expected value? That is not a true value. True value means you have to analyze all the data and then to get the true value. But we call that as expected value because we are just analyze our group, our sample from the population. So that's why in discrete random variable, we call that as expected value. And but expected value, if you look at the graph, they are actually not even uniform as as this one. Okay, let me circle as this one. If you have a uniform one, yes, you have a very accurate expected value or mean to represent your data, but actually in real life is not actually. So therefore we need variance. We need variance to see what is the variables, in the data, and how the spread is our data spread around, how far our sample, our data, that select data is close to the mean. This is what we are looking for. Okay, so okay, if you look at the top part is the discrete random variable, the green one, and the continuous is the yellow part. Okay, so and actually this one, the exponential is actually belongs to continuous random variable, but it's all right. We are going to learn it for our next week onwards. Okay, so yeah, like I mentioned to you, this section we are going to learn a lot about mean, variance, and so on. This is kind of like a summary on it, and I need to yeah. And among these, okay, 1, 2, 3, 4, 5, 6, 6 of them are the most popular family for discrete random distribution. And of course, there are others for a special case, but for your standard, we're going to learn only these 6 of them. Okay. So a lot of people confuse about Bernoulli and binomial. So Bernoulli is the difference between them is actually the number of trial. So the Bernoulli is just one trial. What is the first trial? Then I can get my successful outcome. And my outcome should be 2 variables. Two outcome, success, failure, on, off. So only binary outcome. Whereas for binomial, you can try many, many times. But again, your outcome is still binary. Okay, when you try many, many times, you have more than one time of number of success. So for example, I want to try 5 times, okay, and I would like to know what is a successful rate for me to just flip the coin. 3 of them is head, and out of 5, so my successful rate is 3/5. Okay, so it's quite simple, right? Okay, so that is the binomial distribution. So let's have a look on one example, Bernoulli distribution. Let's say I would like to try my old car signal. Okay, so I represent the x as the signal on equals to 1. When the signal is not able to on is 0. Okay, so remember that the successful rate plus the failure rate, it's always equals to 1. So let's say, see, I just cut it off, I just left 1, right? Okay, so when I draw it into histogram or PMF, so I have my x equals to 0, and because my failure is 60%, is obviously it's an old car, so it's 0.6, my px or my fx. My x equals to 1 is 0.4, okay? Is that clear? Okay, so next, we try, have a look at an example of binomial distribution. I give you an example like everyone loves chocolate. A candy company produces dark and milk chocolate. So I have success. My x is equals to 0 if dark. My x equals to 1 is milk because I'm looking for milk chocolate. Okay. So my successful rate is P is 0.5. My N is 10. Okay. I would like to have the PMF diagram on this part. So then my probability distribution equation for this is N combination R successful rate power of X, Q, the failure, the total of trial minus the X. So it's quite simple. Let's try let's say try number of success is 0. So I have tried 10 times trial. I have none successful rate, and I have 10 fail. And to get my percentage of milk chocolates is power of 0 because I don't have any. To get the failure is I have 10. So you will get your number is quite close to 0. That's why you can't see much. Okay, then you can try using the x equals to 1. When x equals to 1, okay, p x equals to 1, p x equals to 0. Okay, so you plug it in, so you can realize that you will get quite a little bit of number 0.009 if I'm mistaken. Try it out. So and then you just keep on trying it until 10, and then you can get your PMF. So the mean expected value is n times p. So in this case, my n is equals to 10 because I have 10 trial, right? So light green, so 10 trial times the successful probability is 5. Okay, for the variance, n is 10, p is 0.5, n is 0.5. So what is the number? That is your variance. Okay, is that clear? Okay, so this is the summary, the general things. If you are writing a notation on the Bernoulli, you have to y. Okay, you just write like this, y, ver, p. Okay, the p is probability of success. So like just now, the chocolate bar is 0.5. So my successful is 0.5. Okay, so if your work is binomial, so y bin, and you have how many trial? N is trial. I have 10 in just now, and my successful rate is 0.5. Okay, is that okay? So for the mean of Bernoulli is P. Your successful rate is your mean. For the variance is, because you only have one time, so basically there's an n here, but your n is equals to 1. And therefore you have this equation. And whereas for the binomial, you have many trials, so you have n in the front. And in this case, you have n equals to 10 in our previous example. Okay, so this is some of the example. Try it later, and we can discuss again in the tutorial. Okay, try it first. Also on these two example and trial. Okay, and it's quite straightforward. The one that we should discuss on this question is let's try this part. Is sample of 25 bar. So this is N25. Okay. So typically 1% of part is required rework. Okay. A process problem is suspected if X exceeds its mean more than 3 standard deviation. Normally we deal with 1 standard deviation, but in this case, we are looking at 3 standard deviation. Okay, so look at this one. So like I mentioned to you, this one, because it's n is equals to 25, is definitely not binomial. So we know that we are going to use Bernoulli. We are not going to use Bernoulli, but we are going to use binomial. So like I mentioned to you just now, the equation for the mean is NP, the expected value. So it's quite fast, okay? NP, the P is 1% of parts require rework. So, yeah, okay? So your P is 0.01, so your expected value is this. Your variance is NMP. You still remember? M P Q, or we can use it as you can write it as 1 minus P. Okay, so we just put it in. That is your variance. And but in this case, if you look at this, my X is mean plus 3 standard deviation. Right. So I need to find this first. Okay. So I have my mean. I have my variance. I can find my standard deviation. So then my X equals to 1.74. Okay. Back to the question. The problem is suspected if X exceed. So the X exceed this one. So therefore, I write X bigger than 1.74, right? So because this is a binomial, right? So our X is close to or equals to 2, or I should say 1 minus X smaller than 1, okay? So when we do that, we have 1 minus P X equals to 0 plus P X equals to 1. Okay, so and therefore you have this calculation, and this is your answer. Try it out. Okay, and the next one, if the percentage of pass is increased to 4, so now my P equals to 0.04. What is the probability that X equals to 1? Okay, that is tricky. So now is, if my N is 225, my P is 0.04. Okay, what is the probability that more than 1? I would say 1 minus X smaller or equals to 1. And is in this part, same thing, because 1 minus Px equals to 1. Oops, 0 and 1. Okay, so you have the you have quite similar answer, but it's different because of your P change. Okay, so next, if your percentage part increased to 4%, so P equals to 0.04, what is the probability of X bigger than 1 in at least one of the next 5 samples? So what is the probability X equals to 1? And at least of the next 5 samples. Now I just focus on the first 5 samples. So means my N equals to 5. My P equals to 0.04. Okay. So I'm looking for Px bigger than 1. Okay, so next I look at this. If you look at this, we are no longer use x because the sample size is different, it's no longer 25. Therefore, we try to use another one to represent it. Okay, so and if you look at this, okay, it's still binomial, and my n is 5 instead of 25, and my successful rate now is, okay, because I am sharing the successful rate same as the B, correct? So my successful rate for x equals to more than 1, 8.264. Is that okay? So in order for me to get my y more than 1, so it's equals to 1 minus p y equals to 1, 0. And therefore you can get 0.7843. Okay, I know it's a bit too heavy for you, but if you can try, have a look again, at least 2 times, that will be easier for you to understand and solve this problem. It's just play around with your understanding. Once what I can say is once your n change, so you can't follow the previous one because your sample size is different. Okay, is that okay? And your successful rate is the same, like this. Successful rate is P.04, but your sample size is different. Okay, so therefore your P change. Okay, so try this. If you can't or you need any question, we can discuss in our next lecture again. So next, besides binomial, multinomial is a distribution that analyzes the outcome that more than 1. For example, the very common example is you play the deck. So there is spread, heart, diamond, and club. All right, there are 4. So when you have more than 4 outcomes, so it's actually quite simple. Let's say I have 10 trial. This is the number of trial. So successful for the first one, successful for the second one, successful for the third one. Here, the number occurrence of the outcome. So P is the successful rate for the X1. P2 is the successful rate of the X2. And PK successful rate for the K. And for the mean and variance for the multi-binomial is quite simple. Okay, so you need to find the multinomial successful rate, the PI. Okay, so I'll give you an example, and it's quite similar to the binomial mean and variance. Let's have a look at example. Okay, suppose a card is drawn randomly from an ordinary deck of playing cards, then put back in the deck. The exercise is repeated 5 times, so I know that I did 5 times. What is the probability of drawing 1 spade, 1 heart, 1 diamond, and 2 clubs? I know that I have tried 5 times. Okay, yes, my n is 5 times. So the n for me to get the heart spade is 1, heart 1, 1 diamond, and 2 club. Okay, so the probability for each of them is equal, is 0.25, right? So what is the probability of this event? So the probability for us to have this drawing 1 spade, 1 heart, 1 diamond, and 1 club is So you use this equation, amount 5 trial over the 1 spade, 1 the heart, 1 diamond, 2 club, times the successful of 1 spade, 1 heart, 1 diamond, and 2 club. So this is your P. Okay, it's quite straightforward. Yeah. So just try, and if you have problem, just come back to me. Okay. Let's try another one. So suppose we have a bowl with 10 marbles, 2 red marbles, 2 green marbles, and 5 blue marbles. Okay. So we randomly select 4 marbles from the bowl with replacement. What is the probability of selecting 2 green marbles and 2 blue marbles? So I quickly write it down. Okay, I have 10 marbles. Okay, 2 red, 3 green, and 5 marbles. Wait, it's just describe the bowl. I randomly select 4 marbles, so my n equals to 4 with replacement. So yes, I can use this. What is the probability of selecting 2 green and 2 blue? So I have, let's say, n1 is red. I don't have red. I have 2 green. I have 2 blue. Okay, so my probability for me to get the green marbles, okay, is 2 out of 10. Probability for me to get the green marbles is 3 out of 10. Probability for me to get the blue marbles is 5, because I have 5 marbles. Okay, so among 4 trial, I have none red marbles, 2 green marbles, 2 blue marbles, and these are the successful rate of each of them. By plugging in, I can get my probability of selecting 2 green marbles and 2 blue marbles. Isn't it quite straightforward? Okay, so we have learned about Bernoulli distribution, which is one trial, binomial distribution, which is multiple trials of Bernoulli, and both of them have binary outcome. We also have the multiple distribution, which is we have more than 2 outcomes. And now we are going to learn about geometry distribution. So it's negative binomial and geometry distribution are quite close to each other. I would say it's quite confusing as well. So let's have a look at the example. Geometry distribution is number of failure before the first success. Number of failure before the first success. So I'll give you an example. I toss a coin, okay, until I land on the first head. I try, I don't know how many times I try, okay? So I try until I land on the first head and stop. That is geometry distribution. Negative binomial distribution is, suppose we flip coin repeatedly, keep on repeated, count the number of head success. If we continue flip a coin until it's landed 2 times of head. So number of failure before n success. I'm looking for more than 1 time of success. How number of failure before the n success? What is the probability that I flip a coin until I have 2 success? That is negative binomial distribution. Okay? So let's have a look on the negative binomial distribution, the equation. Okay. The x is referred to the number of trial required to observe R success. So let's say I have 10 trial, 10 minus 1. Combination R minus 1. So for example, I want to try 10 times and I need 2 success among the 10 times. So x minus 1 combination R is 2 because I'm looking for 2 success. minus 1. So our R is 2 here. Let me write it down so easier for you. Let's say I would like to have a 10 trial, and among the 10 trial, I need success of 2. So x equals to 10 minus 1. R is 2 minus 1. R is 2, x is minus 2. Okay, so same thing like just now. Okay, so 9, among that I have 1, another 1. What is that? Another one is, let's have a look on this one. Another one is C minus 1. Okay, so when we try on this part, right, so we can write it as 9 and 1. Okay, so I have my rate P over 2 Q. Q is the failure rate, 1 minus P, and is 8. All right, so like I mentioned to you, I have 10 trial, and I would like to have successful for 2. So for the negative binomial random distribution, so I have this equation, and then you can try to find out the value for this. Okay. Okay, for the mean and the variance, okay, it's quite straightforward. The R is what you are looking for. In this case, we are looking for R is 2, P is the percentage of successful. And whereas for the variance is R, in this case, we have 2, Q is the failure, okay, or I can write it 1 minus P, because Q equals to 1 minus P, or P plus Q equals to 1. Okay, and over the P power of 2. That is the variance for negative binomial. Okay, so this is the example, one of the example. Bob is a high school basketball player. He is 70% free throw shooter. What is that means his probability to make free throw is 0.4. During the season, what is the probability that Bob makes the third free throw on his fourth shoot? So next, then we go back here. Number of failure before the number of success you are looking for. At this part, okay, the question is, number of trial is 4. Number of success is R is 3. Okay, the R is 3. The P is 0.4. Okay, in this part, you might ask, is this geometry? Is this a geometry, or is this a negative binomial distribution? Well, number of failure before the first success. Then we look at this. This is the third free throw. Means that the success for him is 3 times already. So R equals to 3. So, and therefore, this is negative binomial. So I just put in the value. So I know that I have tried 4 times, and successful rate is 3 among them, and my successful rate is 0.7. My R is 3. 0.3 power of my x is 4 minus 3. Okay, so this is wrong. This is 4 minus 3, and then here you go, you get your answer. Okay, so yeah, you can try the next one, and we can discuss it in our tutorial again. So we have another trait distribution to look at, okay? So the geometry distribution that I mentioned to you just now, go back to the summary. Geometry is number of failure before the first success. So what is the first success after you try many times? And you know that my successful time is just 1. So, and when we use the negative binomial equation, the R is 1, R minus 1 is 0, so we just cut this whole thing. It actually equals to 1. So when we try to remove this, okay, then we can remove this part. And we can have, therefore we can have this equation, okay? Is that okay? Because R is equals to 1, therefore X minus 1. And therefore you can have this equation. It's quite straightforward. Okay, so the geometry, like I mentioned to you, the first example, the Bob example, what is the probability that Bob make the first 3 throw on the 5th stroke? So we know that our X is equals to 5, number of success is number 1. So R is 1, P is 0.7. So we just put in our PX equals to 1 equals to P. What is our P? 0.7. Q is 0.3. X is 5 minus 1. Okay, so this is, you can just cut it off, and therefore you can get this answer. Try it out, okay? And so just now we learned about binomial. Binomial is you try so many times, and then it's every time it's independent, means that after you try, you put it back and it's independent, right? But hypergeometry is you have tried, but you never put it back. So it's dependent. It's dependent. The second trial is dependent on the first trial. Okay, so there's a difference between the hypergeometry and the binomial geometry. If you look at the binomial number of trial, okay, probability of success, Q is probability of failure. So for hypergeometry, N is number of population, number of trial is R, number of success is A. In this case, okay, I just happened to find this. Yeah. So the difference, like I mentioned to you, is they are dependent. If you take out some lucky draw, for example, you take it out, you're not putting that back. So you are doing hypergeometry. And there is another one rules for this. Your different alignment element from among the big elements. So your selected sample over the big population, it should be more than, the ratio should be more than 0.05. And you are doing sampling without replacement. Okay, so just now we learned about, you have run, you have 10 marbles, 5 red and 5 green. You randomly select 2 marbles without replacement and count the number of red marbles you have selected. This would be hypergeometry experiment, for sure, because you're not putting it back. So the equation for it is quite simple. So number of success is at the top now, is different compared to the geometry or negative binomial. So X is the number of success in the element, the small element, the sample, the total of number of element drawn. Okay, so the mean and variance for the hypergeometry distribution is N is the number of element drawn, R is the number of success over the total number of element. For example, I have we draw 10 times, okay? Like I mentioned to you, I have 10 marbles, so the big N is 10. And then I draw out two marbles. The small one is n, 2. Number of successful in the n element, the number of successful, number of, count the red number of you have selected. So it might be 0, 1, or 2, correct? So the number of success in element in this example, it's your x is okay. We do it like this. Our R number of success in the big element. Our X is number of success in the N element. N, big N is the total of element. Total is 10 marble. N is number of element drawn. Number of element drawn is 2 marbles. 2 marbles, and I would like to have, okay, among this, I would like to have 2 marbles. And from the 2 marbles, I get X equals to 1. Okay, is that okay? It's quite confusing in this part, quite challenging now. So never mind, we have a look on the example, and then we move to the other one. Suppose we randomly select 5 cards without replacement from an ordinary deck of playing cards. What is the probability exactly 2 red cards? If you not necessarily need to involve money. If you have a deck of playing cards, they have the diamond. I remember the diamond is black, I think, and spade. Okay, something like this. And we have the love. What else? I think this one is red. Okay. And another one I can't remember. Let's have a look. So exactly two red cards. So there is a probability for us to get the diamond and the heart shape. So let's have a look on the example, the solution. So in this solution, okay, so we know that our n is 52. In the play cards, there are 52 of cards. And among all the 52 cards, there are 26 are red cards. Okay. N is the 5, you choose 5, right? X equals to 2 because you are choosing 2 red cards. Okay. Okay, is that clear? So you have 52 deck playing cards. You have the chance to get 26 because you're looking for the red one. Okay, from the 26 for the overall, you are only selected 5. And from the 5, you have 2 of them are red. So we plug this value into this one. Okay, and then you can get your answer is this. So your question might be, how I put the value in there. Okay, so we can do it slowly. So we know that we have the R is 26, and we are getting only 2 times the big one is 52 minus our R is 26 combination n, the small n is 5 minus 2. Okay, so the big N is 52 and the small n is 5. Basically, what they do is actually from the 26 red card, I select 2. From the non-red card, okay, I select the non-red card, the rest is the 5 because you have totally 5 over 52. Among 52 cards, you select 5 cards. Isn't that simple, right? The formula look complicated, but when you try to understand it, it's quite simple. I repeat, yeah. Among 26 red cards, I choose 2 times the rest of non-red cards, also 26. From the 26, I select 3 because I need 5. And 52 cards, among 52 cards, I select 5. From there, you can get your probability random variable that you select 2 cards. And you can also put it in to try to find your mean and variance, okay? Okay, so now we go for Poisson distribution. Poisson distribution is quite interesting Poisson. It's commonly used for example, insurance. They are looking for a very rare event. For example, what is the probability for the person to get cancer? I know this is quite common now, but when you look at the major population, so its probably is actually not that much. And when we look at the number of try, we don't know. The probability we don't know. Did we replace it? Yes. When we use it, when we would like to find something that we have a ratio of time, selected ratio of time, and we would like to find the probability that on this range of time that my probability that happens higher out of the range. What is that? For example, number of okay, in Malaysia there are, let's say, 80 out of 100 of people infected by COVID. Okay, so what is the probability that we have 100 out of 100 of person infected by COVID, for example? So this is on that part time, we are trying to look at the Poisson. Okay, so like I mentioned to you, Poisson is how to say that? Poisson is quite simple to use it. It's your mean and your variance is depends on the lambda. For example, the mean that your cats bring back a mouse to you in a week time is 1 cat, 1 mouse. What is the probability that your cat will bring 10 mouses to you in this week? You catch 10 rats to you in this week. In this kind of condition, you are going to use Poisson distribution. Okay, so so when we look at the equation, the lambda is your mean, the e is the base of natural logarithm, and the x is the number of events occur. I found that this is a good explanation. This video have a good explanation on Poisson. So, and it's quite fun to check it out later. Okay, so example, let's have a look on the example. The average number of homes sold by the agent is 2 homes per day. What is the probability that exactly 3 homes be sold tomorrow? So it's quite rare, isn't it? you are normally selling two houses, but you are looking for the probability that you are selling higher than that. So in this time, we are looking at the Poisson distribution. So another question is, can we use Excel to plot the Poisson distribution curve out? Okay, so I give this as a tutorial. I will list it down. Try it out, and we can look forward to on Thursday to discuss it together. All right. I hope this lecture won't that not too heavy for you. I know it's too much to trying to cling together, but you just need to remember some of the keywords on that. You don't need to memorize the equation. You just need to know when to use the correct equation. That's it. All right. Okay. Thank you, everyone.